Hey folks, how's it going? This is Mr. Moray coming to you with a little video on applying trigonometry through bearings problems. Okay, so yesterday you guys got started by looking at some examples of bearings. You watched a video talking about the general idea of when you're given a description like n 50 degrees east, how do you figure out what that looks like? And so where we're going with that is we're now going to try to actually do some bearings problems, okay? And so basically, these are going to involve applying some of the trigonometry that we have learned thus far, okay? This is definitely a really difficult application, but actually a pretty relevant one that is used particularly in navigation. All right, and so definitely something worth talking about. So we'll work on it over a few lessons, hopefully, and we'll build some real some strength in it. All right, so just to recap, just remember, so the first letter is where we start by looking at. So if I'm standing here, I'm looking north, and then what happens is I turn east by 50 degrees. Okay, so that looks something like this. So I'm 50 degrees east of north. Okay, similarly, I could be 30 degrees west of south, right? I could be, that would be the red one. This says 40 degrees south of east. This is 40 degrees south of east. Okay, and then finally I've got 40 degrees north of west. Okay, so this is 40 degrees north of west. Some things we just might want to recap. First of all, to go all the way around, we know that that is 360 degrees. To go a quarter of the way, we know that's a total of 90 degrees. And to go from north to south all the way halfway around, that would be 180 degrees. So what you might have noticed is that this does go back and hit on supplementary angles, which add up to 180, and complementary angles, which add up to 90. So for example here, to say 50 degrees east of north is the same as to say 40 degrees north of east. And notice how these are complements of each other. But also, we could say, all right, 130 degrees, because if you add the 40 and the 90, you get 130 degrees. 130 degrees, okay, east of south. So lots of different ways to write bearings. The other thing I want to talk about, and this may not have come up, is what happens when you aren't given letters. So usually in navigation, my understanding is that they don't use these letters. And all they use is they start with north as their fixed point, as their kind of reference. And then everything is described in terms of going clockwise from north. So when you don't see letters in front or after an angle measurement when we're talking about bearings, what we're going to do is we're going to assume that it's based on north and we're going east from north. So this would be 40 degrees east of north. Okay, something worth thinking about. And that will come up in the worksheet that we're going to do today, as well as in problems in general. All right, so I'm going to spend the meat of this video looking at a few different word problems. Feel free to go through them and kind of do them as needed. You're always welcome to pause and try them on your own. But then by the end of today, the goal is for us to get started with solving bearings problems. All right, so I'm going to show you the first one. All right, so I'm going to now start by trying to figure this one out here. Okay, so here's what I have. What I have is this. So I have a ship leaves port at noon and heads due west at 20 knots or 20 nautical miles. Sometimes when you're talking about ship movement, they use the word knots. Doesn't mean like a knot, like you got like a knot in your shoelace. It means nautical miles. Okay? And nautical, because usually we're talking about or read nautical miles per hour, because usually we're talking about a ship sailing over the water. All right? And essentially, though, it's going to cover 20 miles of water. It's going to go 20 miles across the water each hour. Just like if I'm driving my car, I'm going 50 miles an hour. I'm going to cover 50 miles of road for every hour that I drive. Okay? So at 2 p.m., the ship changes course. Okay? And now it's going north 54 west, meaning 54 degrees west of north, as shown below. And this figure isn't drawn. It was drawn in the original problem, but it was not drawn for this example. So for this example, we'll draw it on our own. We need to find the ship's bearing and distance from the port of departure at 3 p.m. So what I'm going to do is I'm actually going to cross out bearing. Because right now, let's just focus on figuring out the distance, and maybe we'll tackle the idea of the bearing from the final point a little bit later. All right, so let's draw what this looks like. So here's my port, and when you see the word due west, what that means is purely west. It's not angled up. It's not angled down. It's going straight west. Okay, that's important to know when you see the word due. Okay, like due north means it's just going north. And at 2 p.m., we're going to engage. So let's take a look at what we got so far. So far, it's gone 20 nautical miles per hour. It leaves at noon. So here's the point where it's going to go ahead and change position. And it's going to start going in a different direction. Okay? But how far has it gone so far? Well, it was going 20 nautical miles. By the time it changes direction, it's 2 p.m. So it's 2 hours. So it's gone 40 nautical miles from the port to the point where it changes position. But where does it go? So here's what we do. When we change direction, what I'm going to do is I'm going to put my north here. I'm going to draw it with a dotted line because it's not part of the triangle I'm going to create, but it's good for reference. Okay? We know that this is west because why? Because we're going due west, right? So that's my west. And so I'm going to go 54 degrees west of north. So the effect of that is that I'm going to go in this manner right here. Okay? And so what this is 54 degrees west of north. Now, this is not the whole angle. Important. This is only this piece of the angle right here. What you may have noticed, however, is that this is contributing another 90-degree angle, and we're going to see how that plays out in just a moment. Let's finish this. Now, this is kind of blocked, but what we know is that this is the point where we want to know exactly how far has this ship gone. And I'm going to put this in black so we don't get it confused there. Okay? So at this point in the game, what I have is this. I'm going to do this in a different color so this doesn't get confused. Okay? At this point, the blue represents how far have I gone at 3 p.m. And also because I've gone another hour and there's nothing to indicate that the speed has changed. My apologies there. There's nothing to indicate that the speed has changed. what that means is that this is another 20 nautical miles. And now I need to figure out what this is. Okay? And so what I have is I have angle, side, angle, side, given information. And there's not enough angles to use the law of cosines. All right? And because this is not a right triangle, what we know is that SOHCAHTOA does not apply. So what I'm going to use the law of cosines. Again, law of sines, not enough information known. I would need another angle that I don't have. SOHCAHTOA, it's not a right triangle. So I now need to do this. Now, the biggest thing that throws people off is a lot of people are going to set up their law of sines and they're going to say 54 for their angle. But you would actually be wrong because I need to know this whole angle here. Okay? Because remember, when I turn at this point, I'm only making the 54-degree angle relative to being due north, okay? So I also need to take into account the 90-degree angle here, and so I would add those up. I would be 90 plus 54, and even though figures aren't drawn to scale, hopefully we have a sense, all right, that this is an obtuse angle. It's clearly more than 90 degrees. 144 seems to back that up. So to find the distance, what I know that the distance squared is equal to 20 nautical miles squared plus 40 nautical miles squared, okay, minus 2 times 20 times 40 times the cosine of 144 degrees. All right, so let's figure that out. So I've got the distance squared equals 20 squared, which is 400, plus 40 squared, which is 1600, minus 2 times 20 times 40. And we can actually see what that is. And that's also 1600 cosine of 144. So I'm going to do this on my calculator. 400 plus 1600 minus 1600, making sure we're in degree mode, not radian mode, which hopefully we should not be in. And that gives me that the distance squared is approximately, let's call it 3294.427 nautical miles. And that's not really necessarily, let's just forget the units right now, because what we need to do is we're going to take the square root, not technically of the answer. If you want to, you can, but then you've got to readjust what you're writing on paper because you're going to get a slightly different answer. And I'm just going to type in the 427. And so what I get is the distance is approximately 57.4 nautical miles. Okay? So in other words, the distance that we've traveled from the port, if we're right here, is 57.4 nautical miles. And if you think about it, right, first I'm shooting 40 degrees away, but then as I go up, I'm moving not only north, but I'm also continuing to move west. So that is going to contribute there as well. All right. So please make sure you understood how I did this one. Make sure this all makes sense. Remember, the trickiest part is a couple things: setting up the diagram and also figuring out how to piece this together. All right. And then once you're ready, go ahead and move on, and I will show you how we're going to do the next problem. All right, here we are at the next problem. Hopefully that one made sense. A ship leaves port at noon, having a bearing of south 29 west. The ship sails at 20 knots, which we now know is nautical miles per hour. At 6 p.m., the ship changes course to due west Find the ship's bearing and distance. Again, let's just focus on the distance for now. From the port of departure at 7 p.m. So similar problem. So please, please, please help me out, because I promise you by the time we get to some kind of unit assessment on this, okay, you're not going to be given a picture, and it's going to be really important to draw a picture, as with many situations. All right, so let's make a picture here. So here's my ship. And let's get a sense of what's going on here. So here's my north. I'm actually going to reorient this picture because I just realized that we're going west of south. So I'm going to start here. And here's my south, right? I know this would be due south. And I know that this would be due west, right? And so what's happening is I'm going to go, my ship's going to go 29 degrees, okay, west of south, all right? And then the ship is going to sail 20 knots. It's going to go and go and go. And so remember, we're leaving at noon. At 6 p.m., it's going to be changing course, okay? And so what happens is, let's start by looking at how far does this thing actually go. So it's going 20 nautical miles per hour. It goes for 6 hours. So it's going to go a total of 120 nautical miles. Now, at 6 p.m., and this is my strategy for you. Every time you get this direction change, start with your point and reestablish your north, south, east, west. I promise you, because look, I was doing these problems and I was literally going out of my mind. Like, I don't get this at all. And then my savior, Mr. McCready, pointed out, hey, Mr. Moray, why don't you take a second, man, and why don't you actually set up the directionals as it changes? And that literally blew my mind how much of a difference it made. So please, I'm telling you, as someone who struggled with this, just like you potentially, there's nothing wrong with that, okay? But this is why I'm giving you these strategies, all right? So I reset my directionals, and this represents due west, right? Because this straight up would be north. And so look, what I know is this is 90, but what is this? Well, maybe you noticed that if you think about it, no matter how you navigate, right? North, south, east, and west, that's not going to change, right? North is always quote unquote up, south is quote unquote down, right? And east and west. So if I was to have a directional here and I was to have a directional here, well, the north, south are going to be parallel to each other. So effectively what I have is I have a line cutting through two parallel lines. And what we know is that because this is 29 degrees by alternate interior angles, because these are on the inside, this must also be 29 degrees. And I'm telling you, when Mr. McCready pointed that out, I literally went bonkers. It blew my mind. So please set it up as you go. And I'm telling you, because I tutor people in other subjects other than math, like computer science, the best thing you can do for yourself when you've got these difficult problems is to literally take them step by step. That's the number one trick that works. It doesn't matter if you're doing math, computer science, biology, just take it step by step. All right. Now I know it's going to go. I need to know when it hits this point, right? Now it's 7 p.m. So here I'm at 6 p.m. I go another hour, which means I need to go an additional 20 nautical miles because I know I'm going 20 nautical miles every hour. And now I need to figure this out. Again, it's Law of Cosines. So notice, this is 29. We know this is 90. So that means that the angle that I want is 90 plus 29 for a total of 119 degrees. So I'm going to make note. I'll do this in blue. This is 119 degrees. So let's set it up. Now, remember, I haven't specified the angles or the sides or anything. So like, you could memorize every single law of cosines, but if you think about it, this is the only thing you need to know. The distance squared, right? So I'm literally just plugging in the other two sides, right? My little sides. Okay. And then cosine of, and I just want to move this so it doesn't get, so we can still see that navigational picture there in case I post this. What's my angle? 119 degrees. Okay, so I'm doing 20 squared plus 120 squared. So the difficult part with this is basically setting up the triangle. Once you set up the triangle, I've got a strong amount of faith that we're going to really kill it with the law of cosines. Cosine of 119 degrees. Giving me that the distance squared is equal to 17,127.086. And then I'm going to take the square root of just that. Okay, and again, don't go nuts with the, if you want to use all the decimals, that's fine with me. If it's on a test or quiz, if you could just please make note of what you're square rooting, that would be helpful to me. So making note that, right, oh, that's what I'm rounding to, right? All right, and so I should really use approximate. So the distance is approximately 130.9 nautical miles, okay? And so again, what we're doing is we're breaking down the problem, we're setting up a triangle, and we're using the law of cosines to figure out that remaining side. Okay, so please make sure you understood how I did this. Again, we're going to build up these bearing problems nice and slow. We're going to take our time. We're going to build them up. Don't worry, we got plenty of time. We got a few days to build this out. So just give it a chance, and I know you can do it, okay? Don't get upset. Don't get kind of stressed out. These aren't easy, but if you stick with me and you kind of approach it with a focused mind, you kind of put away that anxiety for a minute and you say, look, everything I need is right in front of me, then I know we can do this one. All right, so here we go. I'm going to move on to the next one. And from city A to city B, a plane flies 650 miles at a bearing of 48 degrees. From city B to city C, the plane flies 810 miles at a bearing of 115. Find the distance from A to C. So in this one, notice what they did not give us. They did not put letters before and after. So that means by default, we're going to assume that these are our bearings. Okay, because if we're not told otherwise, we're starting at north and going east. So here's my city A. All right, and remember, you always put your navigationals in there. So I know that my references are north and east. And I'm going to start by going 48 degrees. It's a little bit more than half. And I'm going to label that right there. 48 degrees. All right. And it's going to travel. And it will go ahead and touch down at City B. Like it's like a connecting flight. I don't know if you guys have ever taken one of those flights that's like connecting and it like stops. And then some people get off, but maybe you stay on, something like that. Like it's dropping off their passengers. All right. And now we're going to go ahead and we're going to go. I have to set up our navigationals again. Remember, take my advice here. Reestablish the navigationals. And now we're going 115. So we're going to go from north. We're going to swing past the east because this, remember, is only 90. So look, 115, if I take away that initial 90, okay, what that means is that I'm actually going to go 120 25 degrees beyond that. Okay? And it's going to travel, and hit C. And now my goal is I want to find this distance here from A to C. All right? So this is why I promise you, if you can set up your navigationals every time, it will become exponentially easier. All right? And so I know this is, I'm going to do this in black. So we're told we're going 650 miles, and then we're going another 810 miles, okay? So folks, as always, I think the biggest thing people do is they see a lot of words and they start to freak out. But I think you gotta put mind over matter. You have to believe me that everything you need to solve the problem is right in front of you. It has to be. If I don't give you the information, you can't solve it, okay? But what is this 115? Like, why does it even help me? Well, remember, okay, what we have is that essentially okay, if I continue this on, we have a transversal. This is a tricky one, all right? And the reason that this one is trickier than this one is because this one changed to due west. And so it was a little bit easier to put these things together, right? This was like 29, and I just used alternate interior. This was 90. It was a little bit easier to figure that one out. You're going to have to think about this one. So again, try to take a look at this, and if we can extend this, think about this as a transversal here. Okay? So this is one. This is the other alternate, but this angle here, that's not part of it, so you can't use that. Okay? This is where it gets tougher. Only this is 48 degrees, not the whole thing. Because think about it. You can see, based on how I drew my transversal, okay, this part of the angle is not on the interior, right? This, between the black lines, that's the interior. So only this part is 48. That's how this gets tricky. And how do I figure out the rest? Well, it's supplementary angles, right? Because the black line that I drew in the middle at city B here, right, that represents south, well, look, this is 180 degrees. So if I've gone 115 degrees here, well, what's left? So I'll take 180, I'll subtract 115, and I'm going to get the supplementary angle. Hopefully I didn't say complementary before. If I said complementary, I meant supplementary. Good thing there's no one to keep track of all my mistakes. I hope they didn't take that mistake sheet down off the wall. So this is my angle. I've got a 65er from this piece here, the supplementary, and I've got the 48 from this piece here. That is the alternate interior. And that's really the hardest part, folks, because we can execute the law of cosines. It's just a matter of figuring out that middle angle. So I'm going to take my 48, I'm going to take my 65, I'm going to add them together, and that gives me a total angle measurement. Let me do this in green, of 113 degrees. And now we set up our law of cosines, and the rest is gravy from there, right? So let's do it. I'm going to extend my page out, and I'll do this out. So I know that the distance, because basically, guys, once you get the angle, it's the same thing, right? The distance squared what? I'm taking my two sides, 650, 810, right? This part is not any different from what we've done before. It was just a matter of figuring out that angle, and then we're good. Okay, so I'm going to do 650 squared plus 810 squared minus 2 times 650 times 810 times cosine 113. And what I get is, wow, that is nuts. Distance squared is approximately, I think that's 1,490,039 and 878 thousandths. So I'm going to just do square root, and remember to get your answer. If you do second, and then this button, the negative, the minus, right next to the enter, see where it says answer? It's going to take the answer to the previous problem and plug it right in, so you don't have to think about it. And the distance is about 1,220.7 miles. You could make the argument of calling it 1221. In this case, I would accept that because everything else is knocked off to the nearest mile. I'm not going to be too picky if I don't specify, but I think about it, when I round and I call it 1221, that's not really right? Because I'm leaving out the 0.671896. So it's good to have even one decimal reflected in there, okay? All right. So here's the deal. I've gone on for a little bit now. I think this is over 30 minutes. If you feel like you're ready to start the homework, go for it. 100% go for it. Jump right in. The front of it is going to be just setting up some bearing pictures, and the back of it, for the lesson, the first lesson, you are only doing problem 1 and problem 2. That's it. Okay? If you'd like to jump in, go ahead. In a moment, I will walk through how to do problem 1, just in case you need a little bit of extra practice, and watch me do one more before we move on. All right, so make sure you understand this, and then in a minute, I'm going to try problem number 1. Okay, so problem number 1, right? So what we have is a ship is traveling 70 kilometers on a bearing of 27 degrees, okay? And then it travels on a bearing of 147 for another 180 kilometers. Find the distance of the ending of the trip from the starting of the trip. All right. So again, here we go. Do me a favor. Maybe think about highlight that important info. And that's basically what we need. So remember, here's me. Here's my ship. If you want to draw a ship to make yourself feel better, here's my little sailboat. Okay, so please remember, you're going to start by setting up your navigationals. Again, it's not specified, so by default, we're assuming that we're going north and east. So therefore, you're going to set up your north and east. If anyone out there is, I heard, this is, Mr. McCree said this is used a lot in like sailing. So if any of you guys do any sailboating, I'd be interested to see if you've heard of this. All right, and now I'm going to go 27 degrees. So this is 27 north, or rather east of north. Okay, and then I get to this point right here. Remember, see it says and then. So what that means is that the bearing is going to change. And when the bearing changes, you need to reestablish your north and east. Okay? And I know it's north and east because by default, I'm not given letters, so I'm going to assume it is north and east. Now here, basically what we've got is this actually blows past the angle. Okay, so what I end up with is so this is the bearing. Okay, this is going to be 147 degrees. So it's actually, as you see, remember, because the north, south, east, west essentially is very similar to the XY coordinate plane. Okay, it makes those 90-degree angles where the north-south line meets the east-west line, just like the coordinate plane where the x-axis or horizontal axis meets the y-axis, or sometimes we call it the vertical axis. Okay. And then I'm going to hit this point and I am done. And so what I want to know, and I'm just going to change the color of this. So sorry if that little menu appeared there. I want to know this distance right here. Okay. And so again, it's law of cosines. So let's take a look. So look here, we know that we're told this is 70 kilometers. So basically the problems boil down to either I give you a speed and a number of hours or time period, and then you just have to find the distance, so it adds that additional step, or I explicitly tell you what the distance is. And so this is one of those latter situations where I'm just telling you that. The key is this little angle right here. What is that? So remember, again, I'm going to extend, and if this helps you to do this, you can make your full compass. I'm going to extend this down. Now, the big mistake I made when I was caught lacking on this. Originally, I was like, oh, duh, this is 147 degrees. But that's why you set up the north, south, east, west, because if you don't, you put 147 in your law of cosines, you're way, 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 way off. Okay? So again, we take a look here, and I hate to make a line through my shit. So we know this is 27 degrees, and again, this is a transversal. So if this is 27, this little piece is 27. And again, this line has to add up to 180. So I come in my calculator, and if you can do it in your head, go. That's all right. I don't want to do it in my head, so I'm not gonna. And what I get is I get a 33-degree angle right here. So that adds up to 180. All right. And so what that tells me is that my angle of interest is 33 plus 27, or maybe you've done this in your head as 60 degrees. And so the angle that I want is 60 degrees. Okay? So again, the hardest part of this is that you have to make a picture and setting up that middle angle. But here's the thing, and this is the beauty of math, is it all comes down to these fundamental ideas, right? Transversals, supplementary, and complementary angles. All right? Maybe I'm oversimplifying it with my tone, but if you think about it, what's cool is it comes down to these like ideas that we learned that we're like, oh yeah, we can do those. All right? But it's used in such a complex and beautiful and important way. That's one of the reasons I just really, really love math. All right? Because the simplest things give you the coolest results. And as I do this, I'm going to tell you, I did this summer math program once, right? And we proved literally one of the coolest math statements I've ever seen proven in my life. And all we needed to know to prove that statement was that pi was more than 3. Just by accepting and knowing that pi was more than 3, we were able to prove this really, really cool statement in number theory. It's crazy, right? That pi is greater than 3, like duh, right? Obviously, but yet so much great stuff can be drawn from that. Okay, so before I'm not a good multitasker. I'm really, really not. So I'm gonna kind of shut up here and finish setting this up. So 270, 180, cos 60. So let's set that up. So I've got 70 squared plus 180. I apologize. I just dropped my tablet. Side I would expedite this minus 2 times 70 times 180. And I got to find the keyboard shortcut for cosine. Cosine 60. Okay, do that out. You see it's coming out to a whole number, and the reason that is because actually 60 is a special angle measurement, right, from 30, 60, 90, and so cosine of 60 is actually, I think we might have seen this as a half. Okay, so the distance squared turns out to be a perfect 24,700. How lucky are we? And I take the square root of that, and I don't want to type in 24,000. Oh, but I can't do that. Ugh, darn it. I actually have to do it. See? So that's the problem with doing that. You got to be really careful, because I want to do the square root of 24,700, not the square root of 0.5. And what I get that the distance is approximately 157.2. I'm going to go with a 0.2 kilometers. All right. So folks, thank you so much for tuning in. I know there was a lot to this video. I tried to go slow and really break things down and give you a lot of examples because I know this stuff is not easy. So here's what it comes down to, folks. You need to be able to construct a picture, okay? And no matter what, it's going to be like whether it's a picture like this where you're going due one direction so it's flat, or whether it's a picture like this where you need to use alternating interior angles, or this one, can take the time to make the picture, because when you do, you're going to find that it makes your life so much easier. All right, so folks, best of luck with the work today. We are going to have our hangouts this week on Wednesday. So keep thinking about what questions you might ask. Keep working hard at it, all right? Because in the end, I know, remember, you can do it. All right, thanks for tuning in again. Please feel free to like or subscribe so you can stay up to date on all my videos. Have a wonderful day.